we'll continue with what we were reading in the last class. We're actually studying about the MOSFET. So in this module, that is in the fourth module, we have started with metal oxide semiconductor or MOS capacitor, right? It was called a capacitor because it had two regions, that is a metal region and the semiconductor region, and in between you have an oxide layer, that was metal oxide semiconductor, and it had different modes of operation. As I have already mentioned in the last few classes, we had different modes of operation like accumulation, depletion, inversion, and strong inversion, out of which the property called the strong inversion, that is when the semiconductor is being inverted, that is if we are using a p-type semiconductor, under the condition of strong inversion, we will be having a layer of electrons in the p-type semiconductor at the junction of oxide and semiconductor. So that is actually the property that is being made used in MOSFET or metal oxide semiconductor field effect transistor. In this case, that is the property that we are using, that is strong inversion property. And what is the voltage VGS? What is voltage VGS called when we are getting a strong inversion operation? നമുക്ക് strong inversion നടക്കുന്ന സമയത്ത് VGS എന്ന് പറയുന്ന വോൾട്ടേജിനെ നമ്മൾ എന്താ വിളിക്കുക? What is that called? What is VGS called when we are having a strong inversion? നമ്മൾ in the last class പറഞ്ഞിട്ടുണ്ടായിരുന്നു. Can anyone say? What is VGS called? VTH, exactly. VTH or threshold voltage. That is the voltage VGS at which strong inversion occurs is called VTH or threshold voltage. That's a very important definition. That is, ഏത് വോൾട്ടേജ് ഏത് VGS എന്ന് പറയുന്ന വോൾട്ടേജിലാണോ സ്ട്രോങ് ഇൻവേർഷൻ നടക്കുന്നത് അല്ലെങ്കിൽ സ്ട്രോങ് ഇൻവേർഷൻ സ്റ്റാർട്ട് ചെയ്യുന്നത്, that particular voltage is actually called the threshold voltage. So that is an important condition. That is, VGS has to be greater than VTH. VGS has to be greater than VTH for strong inversion to take place. That is important in MOSFET. So I have already mentioned the different types of MOSFET. We have several classifications of MOSFET, out of which the basic ones are okay. The basic ones are ഏതൊക്കെയായിരുന്നു? രണ്ട് different types ഇന്നലെ പറഞ്ഞിട്ടുണ്ടായിരുന്നത്. Which are the different types of MOSFETs? Basic types. നിങ്ങൾ respond ചെയ്യൂ. See, നിങ്ങൾ ഓൺലൈൻ ക്ലാസ്സിലല്ല, you can respond in your chat or either through mic. Yes, one is enhancement. Everyone has to respond. Okay. One is enhancement. The other one is depletion Mosfet. Okay. What is the specialty of enhancement Mosfet? Enhancement Mosfet is initially that will be in the off state. That is, there will not be any. I will just draw the structure. I have already drawn this yesterday. This structure you need to draw this several times in your notebook. Yes, this is actually the structure of MOSFET, metal oxide semiconductor field effect transistor. So in this case, initially you are not having a channel over here for the electrons in the source to reach the drain, or in order to have a current flow. Current flow is circuit we need to have transfer of electrons from this region, that is from the source to drain. But since this is a P substrate, we are not having a channel over here. So initially, if the MOSFET is in the off state, that is initially if there is no channel present over here, then we need to create a channel over here by applying VGS voltage. നമ്മൾ ഇന്നലെ പറഞ്ഞ എക്സാമ്പിൾ, പൈപ്പിന്റെ എക്സാമ്പിൾ പറഞ്ഞ പോലെ, by using gate we need to create a channel over here. Okay. So initially, this MOSFET is initially in the off state. By applying a voltage VGS greater than VTH, what will happen? Inversion will occur and we will get a channel over. Channel means a negative. Inversion, strong inversion നടക്കുന്ന സമയത്ത് oxide semiconductor energy band diagram നിങ്ങൾ നോക്കിയാൽ മനസ്സിലാവും. Strong inversion നടക്കുന്ന സമയത്ത് oxide semiconductor interface you will be having a layer of electrons. Right, you will be having a layer of electrons at the semiconductor oxide interface. When VGS is greater than VTH. And now you are having a channel for the electrons to move from this region, that is from the source to drain. If you are connecting a positive over here and negative. So the potential that you will be connecting, I don't know whether you can see this. It will be done like this. VDS will be connected like this. Because these electrons has to come to this side. Like, this side is positive. Clear? We will be applying a VDS. Two voltages are there. One is VDS and then is VGS. VGS also has to be positive. This is VGS. This one is VGS and this potential is VDS. VDS, this terminal has to be positive. Even the electrons to move, since we are having n plus regions over here, electrons will be moving from the source to drain. For that, you need to connect positive terminal. Positive connect electrons to move. They will be attracted towards this terminal. And now there will be a current flow through the circuit when there is a channel present. Okay. If initially it is in the off state and then we are turning it into on state by applying VGS greater than VTH, then such type of a MOSFET is called enhancement MOSFET. Okay. In the case of depletion MOSFET, initially this will be in the on state. The initially on state is an enhancement MOSFET. We can only turn off this device by connecting a turn off. Initially, what a layer of electrons on the. We are having a layer or we are having a channel between the source and drain. How will we, turn off this channel? This channel we remove by apply voltage. How can we apply a voltage here? VGS any type of voltage apply this channel. Electrons in the layer. If we need to move this electron layer away from this, interface, what should be the voltage that we apply over here? Positive apply ചെയ്താൽ ആവോ പ്രണവേ നമ്മൾ positive apply ചെയ്യുന്നത് എന്തിനാണ് നമ്മൾ പോസിറ്റീവ് വാല്യൂ അപ്ലൈ ചെയ്യുന്ന സമയത്താണ് ഇവിടെ ഈ p സബ്സ്ട്രേറ്റിലുള്ള minority carriers ആയിട്ടുള്ള electrons you will be having minority carriers like electrons here. p substrateൽ majority carriers ഏതാണ്? Majority carriers are holes and minority carriers are electrons. When we apply positive over here, these minority carriers will be attracted towards this junction. This junction like attracted our minority carriers. Thus our channel form ചെയ്യും. Any minority carriers are electrons. This is actually a negative layer or this is actually a electron layer. Or electron layer form. So in order to move these electrons away from this position, which should be the voltage that we apply over here. If the voltage would apply, the electrons would move out. Yes, obviously it has to be a negative voltage. It has to be a voltage that is less than VTH. VTH is voltage apply. These electrons will move away from this position. This position is moving so that particular channel will get lost. Then it will be moving into the off state. Clear? Initially, if there is a channel present, then such type of a MOSFET is said to be a depletion MOSFET because that will be initially in the on state and we can turn off that by removing the channel from the junction. This interfacing channel remove device turn off. And that can be done by applying a voltage that is less than VTH or by applying a negative voltage. Clear? Type clear or not? Is that clear? Fine. Then we are having another classification. Enhancement depletion two classifications under that. Now, P substrate. I can have a N substrate also here, right? I can have, instead of this N plus region, I can have P plus region, right? That's possible. I can have a N substrate, I can have P plus here. From E case, in this particular case, this figure, which is the type of channel, in the type of channel, whether it is a positive channel or negative channel. In this particular example, which is the type of channel, whether it is a negative channel or positive channel. ഈ എക്സാമ്പിളിൽ whether it is a negative channel or positive channel. Tell me that first. പെട്ടെന്ന് പറ. Yes, it's a negative channel. So this particular MOSFET is called N channel, and N channel തന്നെ you can have enhancement or depletion MOSFET. N channel MOSFET. Okay, so ഇതിന്റെ നേരെ ഓപ്പോസിറ്റ് എന്ന് വെച്ചാൽ N substrate P plus region ആണെങ്കിൽ you will be having a P channel MOSFET. So ഇപ്പൊ തന്നെ you have got 4 different types അല്ലേ? You can many combinations also possible. N channel enhancement ആവാം, N channel depletion ആവാം, P channel enhancement ആവാം, P channel depletion ആവാം. So many such classifications there, but the basic classifications are MOSFETs can be divided into 2 types, can be enhancement or depletion. In case of both enhancement and depletion, you can have N channel or P channel. അത് ഈ രണ്ട് കേസിലും പോസിബിൾ ആണ്. In the case of depletion also you can have N channel or P channel. And what will be this based on? This depends upon the channel we are having. This classification is based on the channel we are having between the source and drain. If you are having a negative channel, it is called N channel MOSFET. If you are having a positive channel, we are having a P channel MOSFET. So this is the basic classifications. Sometimes this can be asked for 3 to 4 marks. But mention the different types of MOSFETs. You can mention the enhancement MOSFET, depletion MOSFET. You can represent the figure and just write the different classifications. And mention the off-on state also. Enhancement initially it will be the off state. Then we can turn on the device by applying a voltage which is greater than VTH. Depletion case it will be initially in the on state. You can turn off the device by applying a negative voltage. So is the classification clear to you? Is this clear? Fine. Now നമുക്ക് ഇതിന്റെ modes of operation similar to that of the different types. നമ്മൾ ഇതിൽ പഠിച്ചിട്ടുള്ള ട്രാൻസിസ്റ്ററിന്റെ കേസിൽ BJT കേസിൽ we had different modes of operation. We had active, saturation, cutoff, and inverse mode was there. In case of MOS capacitor, you had accumulation, depletion, inversion, and strong inversion. Now in case of MOSFET also, we are having some regions of operation that we will study now. Regions of operation in case of, modes of operation in case of a MOSFET. അതിലൊരു 4 ഫിഗർ ഉണ്ട്. 4 ഫിഗറും സിമ്പിൾ ആണ്. ജസ്റ്റ് അത് അതിന്റെ ഒരു വർക്കിംഗ് മനസ്സിലായാൽ നിങ്ങൾക്ക് ഈസി ആയിട്ട് നിങ്ങൾക്ക് എഴുതാവുന്ന ഒരു ആൻസർ ആണ്. ഡെറിവേഷൻസ് ടഫ് ആയിട്ട് തോന്നുന്നവരെ യു ഷുഡ് ഡെഫിനറ്റ്ലി സ്റ്റഡി ദിസ് ടോപ്പിക് ബിക്കോസ് ദിസ് ക്യാൻ ഓൾസോ ബി എ ഷുവർ ക്വസ്റ്റ്യൻ. There is no derivation, only pure theory is there. Be sure about the figures. Don't make mistakes in the figures also. Okay. So for this, you will be drawing 5 figures. Okay, 5 figures. 5 or 4 figures. 4 figures will be enough. The first figure, I'm going to explain the principle of operation of MOSFET. Okay, principle of operation. Principle of, it can be asked like principle of operation or modes of operation or something like that. Principle of operation MOSFET. Don't get confused between MOSFET and MOS. MOS in the case of principle of operation, you need to draw the energy band diagram of accumulation, depletion, strong inversion, and inversion. This is actually principle of operation of MOSFET. Okay, don't forget that. So initially, let me. So I will be using the example of N channel MOSFET. N channel MOSFET I am using an example figure. N plus region. Then you have a P substrate. Then you have the oxide layer. Metal oxide semiconductor. You have the semiconductor, have the oxide layer. Now you have the metal above this. Okay. So this will be your gate. This will be your source. And this will be your drain. Source. This will be your drain. And two voltages will be there. One will be VDS, that is voltage applied across source and drain. Another will be obviously VGS, control the voltage. Here the operation is being controlled by VGS. VGS is the voltage on a principle of, modes of operation control. VGS, two voltages are there, and the current will be obviously ID, drain current. That will be the output current. So we will be controlling the drain current with the help of voltage VGS. Okay, that is with the procedure. So if I am considering this, okay, this is my figure. Now this can be considered as enhancement MOSFET. Okay, enhancement MOSFET I consider because here there is no channel present initially. Okay, initially there is no channel present. Now I am going to tell you one thing which is known to you already, because since we are having a PN junction over here, we are having a PN junction, right? This is P-type material, and here you have N plus regions. What does this N plus indicate? N plus and the indicate in N plus. What does this indicate? N plus, which means these two regions are heavily doped. N plus means these regions are heavily doped. Region. These are heavily doped with negative charges or heavily doped with pentavalent impurities, you can say, because pentavalent impurities will be doping with pentavalent impurities will be giving you the N-type semiconductor. So here the doping concentration is very high. That's why we are giving it as N plus and N plus. So since you are having a PN junction over here, naturally you will be having a depletion region. Okay, no doubt about that. We will be having a depletion layer. I am drawing the depletion layer. Don't confuse this with channel. I am not drawing the channel right now. I am drawing the depletion layer. നിങ്ങൾക്ക് PN junction ഉണ്ടാകുന്ന സമയത്ത്, if you are having a PN junction, we always draw one depletion layer, right? Okay, in a similar manner, I am drawing a depletion layer like this. This is the depletion layer. Don't confuse this with channel. This is not channel. This is the depletion layer of this P and N plus region. PN junction form ചെയ്യുന്ന സമയത്ത് form ചെയ്യുന്ന natural depletion layer ആണ് ഇപ്പം വരച്ചിരിക്കുന്നത്. Clear? Still, I haven't drawn the channel. Okay. Now this is the structure, and when the voltage is less than VTH, that is VGS, the voltage that we are applying. Let me just give the VGS voltage. I'm giving a positive voltage, no issues with that. And here also I am giving positive voltage. Okay, this is VGS and this will be VDS. Clear? Random positive voltage. So when my VGS value is less than VTH, what happens? What will not be present? There won't be any channel present. We know that only when VGS is above VTH, we'll be having a channel present. Only when VGS is raised above VTH, then only we will be getting a channel over here, negative channel. Electrons that can move to the drain like this. Like in a movie, you need a channel over here. Otherwise, you will not be having any channel. Okay. So in this condition, in this case particularly, VGS is less than VTH, and so we are not having any channel. This particular mode of operation is called cut-off mode. This particular mode of operation is called cut-off mode. When VGS is less than VTH, you will be having the cut-off mode of operation. Clear? Clear? Audible ആണല്ലോ അല്ലേ? കട്ടാവുന്നില്ല. Okay. So this is just the depletion layer. നമുക്ക് സാധാരണ PN junction വരയ്ക്കും നമ്മൾ ഈ depletion layer വരയ്ക്കും. In a similar manner, I have drawn the depletion layer like this. This is not the channel. Don't confuse that. So draw this figure. You can draw this figure. Here, even though I have given a positive voltage, നിങ്ങളിപ്പോൾ ചിന്തിക്കും ഇവിടെ പോസിറ്റീവ് വോൾട്ടേജ് കൊടുത്തിരിക്കുന്നുണ്ട്, ഇവിടെയുള്ള മൈനോറിറ്റി കാരിയേഴ്സ് ആയിട്ടുള്ള ഇലക്ട്രോൺസ് ഇവിടെ വന്ന് അക്യുമുലേറ്റ് ചെയ്തു കൂടി എന്ന് ചിന്തിക്കാം. ബട്ട് ദാറ്റ് വിൽ ഹാപ്പൻ only when VGS is greater than VTH. In this particular figure, I have taken VGS value less than VTH. So I will not be having a layer or I will not be having a channel here. So this is said to be in cutoff mode. Cutoff mode എന്ന് വെച്ചാൽ whatever we do, whatever be the positive VDS that we apply, നമ്മൾ എന്തിനാ VDS വാല്യൂ അപ്ലൈ ചെയ്യുന്നത്? VDS പോസിറ്റീവ് വാല്യൂ അപ്ലൈ ചെയ്യാൻ കാരണം ഇവിടെയുള്ള ഇലക്ട്രോൺസ് ഇങ്ങോട്ട് മൂവ് ചെയ്യാൻ വേണ്ടി അല്ലേ? We need to have a flow of electrons through this circuit അല്ലേ? So that we will be getting an ID. But when there is no channel present over here, whatever be the value of VDS that you apply, no use with that, there won't be any drain current. ID will be 0 in case of cutoff mode. Okay, ID will be equal to 0 for cutoff mode, whatever be the value of for any VDS. For any VDS, because there is no channel. Channel ഇല്ലാത്ത കേസിൽ നമ്മൾ എത്ര VDS കൂട്ടിയാലും there won't be any flow of electrons through this. There won't be any flow of electrons from source to drain. That is the first mode, that is cutoff mode. Clear? Can I draw the second figure? Okay. Okay. In this case, the figure will be same. One difference only will be there. That is, I am applying VGS. I am applying a gate source voltage which is greater than VTH. That's the difference over here. Which is greater than VTH. I am applying a VGS which is greater than VTH. Threshold voltage കൂടുതലായിട്ടുള്ള ഒരു ഗേറ്റ് സോഴ്സ് വോൾട്ടേജ്, ഒരു ഗേറ്റ് വോൾട്ടേജ് ഞാൻ അപ്ലൈ ചെയ്യാണ്. And I am considering a very small VDS also. Small VDS I am considering. Okay. So what happens when I am applying a gate source voltage which is above VTH? VTH മുകളിലോട്ടുള്ള ഒരു VGS value അപ്ലൈ ചെയ്യുമ്പോൾ നാച്ചുറലി എന്താ സംഭവിക്കുക? What will happen naturally? എന്താ സംഭവിക്കുക? What happens when VGS is increased above VTH? Yes, channel will be formed. That's right. You will be having a channel like this. Yes, you will be having a channel formed. You will be having a channel formed between the source and drain like this. And you will have flow of electrons through this channel from source to drain. And you will be getting a current ID. This is your VGS. This is VDS. Initially, a very small VDS is applied. and we have provided a VGS which is greater than VTH. When this value goes above VTH, naturally you will be getting a channel over here, channel of negative channel, that is channel of electrons, and so you will be having a flow of electrons from source to drain through the channel. Source to drain. So you can mark this if you can. This is depletion layer. This will be inversion layer. Okay. The red mark that is actually depletion layer, and this is your inversion layer. Inversion layer means this is a P substrate, but you are having a channel of electrons, a negative channel at the interface. So what happens when a channel is present? That's the next question. That is, when we are having a channel like this, we will be having flow of electrons from source to drain, and this channel is acting like it's a conductive channel, so it will be allowing electrons to pass through this channel, and naturally you will be having a current ID, and this current ID linearly increases with the VDS. That is, when we increase the value of VDS, this ID current also will increase linearly initially. Okay, initially when we increase the value of VDS, only VDS value കൂടുതൽ electrons attracted out, right? When we increase this VDS value, now നമ്മൾ VGS ഒരു value set ആക്കി, ഏതാ VTH ന് മുകളിൽ ഒരു value set ആക്കി വെച്ചു. So you have a channel over here. Now what you do is you will increase the value of VDS so that you can have more electrons flowing through the channel and through the circuit. Okay, so when you increase the value of VDS, naturally the flow of electrons increase and the current flow also increase. That is, it's a kind of linear behavior, right? Voltage increasing അതനുസരിച്ച് current increase ചെയ്യുകയാണെങ്കിൽ നമ്മൾ റെസിസ്റ്റൻസിന്റെ ഒക്കെ കേസ് പഠിച്ചിട്ടുണ്ട്. When we increase the voltage, current also increases. So you will be having a linear graph, right? Ohm's law പഠിച്ചിട്ടുള്ള അല്ലേ? This will be a linear figure. So this particular region of operation is called linear mode. So initially when VGS was less than VTH, you mentioned it as a cutoff mode. When VGS is increased above VTH, you're having a linear mode, but only in the initial case. VDS in the തുടക്ക values. Okay, only when VDS is being increased, VDS increase ചെയ്യാൻ തുടങ്ങുന്ന സമയത്താണ് you are getting a linear value. So this particular mode is called linear mode. It's the second mode of operation. That is VGS greater than VTH and very small VDS. Clear? Okay. So I'm moving to the next mode. Only two more figures are there. I will just show that. I'm going to show the third mode. Third mode, third figure. So I am editing this figure. Okay, this figure I edit here. So you have the channel like this. This state. VGS, VTH mode, and now you increase the value of VDS. You are having very small VDS actually, and then you will be having a linear mode. Now if I increase the value of VDS further, okay, that is my criteria. And VGS, VTH mode, you got a channel. Now VGS center roll out. VGS is already raised above VTH, and you have a channel over here. After all, VGS we created a channel so that there is flow of electrons from source to drain. That's fine. Now we are going to use the VDS. Initially, small VDS you were having a linear mode. Now we are starting to increase the VDS value. Okay, we are starting to increase the VDS value. What happens when VDS is increased? How that will affect the structure? That is more important. So here you can see when VDS is been increased, you see that this positive terminal is actually connected to the N plus region, right? This positive terminal is connected to the N plus region. That is an important point, right? നമ്മൾ ഈ പോസിറ്റീവ് ടെർമിനലാണ് എന്നിലേക്ക് കണക്ട് ചെയ്യുന്നത്. എൻ എന്ന് പറയുന്ന റീജിയനിലേക്ക് നമ്മൾ പോസിറ്റീവ് ടെർമിനലാണ് കണക്ട് ചെയ്തത്. സോ വാട്ട് ഡസ് ദാറ്റ് മീൻ ആക്ച്വലി? ഒരു പി എൻ ജംഗ്ഷന്റെ കേസിൽ ഇഫ് യു ആർ കണക്ടിങ് എ പോസിറ്റീവ് ടെർമിനൽ ടു എൻ പ്ലസ് റീജിയൻ വിച്ച് ഈസ് ദ ബൈസിംഗ് ഓവർ ദർ, what is actually happening there when we are connecting a positive terminal? നമുക്ക് ഇങ്ങനെ ഒരു പി എൻ ജംഗ്ഷൻ വരച്ചിട്ട് I am drawing a PN junction like this and I am connecting a positive terminal to N region. What happens? And a positive terminal N region connect ചെയ്താൽ what is actually happening? Which is the biasing that is happening? Tell me that first. ഏത് biasing ആണ് സംഭവിക്കുന്നത്? If I am connecting a positive terminal to the N region, which is the biasing that is happening? ഏത് biasing? PN junctionന്റെ ഏത് biasing ഏത്? If I am biasing like this, if I am giving potential like this, it is reverse biasing, correct? So reverse biasing നടക്കുന്ന സമയത്ത് naturally സംഭവിക്കുന്ന കാര്യം എന്താണ്? First നിങ്ങൾ ഓർമ്മ വരുന്നത് എന്താ? If I am connecting this terminal like this, if I am connecting or if I am providing a biasing called reverse biasing, what is actually happening to the depletion layer width? Depletion layer width എന്താ സംഭവിക്കുക when I am providing a reverse biasing? What will happen to the depletion layer width if I am reverse biasing a PN junction type? Depletion layer width increases. So that should happen here also. Positive terminal, we are connecting that to the N plus region. We are connecting positive terminal to the N plus region. So the depletion layer width has to increase. That has to happen here. The depletion layer width has to increase. But ഇവിടെ ഈ നെഗറ്റീവ് തന്നെയാണ് നമ്മൾ N plus regionിലേക്ക് കണക്ട് ചെയ്യുന്നത്. So if you are considering the VDS voltage, listen carefully. If you are connecting the VDS voltage or considering the VDS voltage, the reverse biasing will be more at the drain end. Positive terminal ആണ് drain end connecting. ഇവിടെ negative തന്നെയാണ് connecting. So there won't be much effect here. So here we are connecting the positive terminal to the N plus region. So the reverse biasing will be more at the drain end. Sentence underline here. The reverse biasing will be more at the drain end because we are connecting the positive terminal to the drain. Right? We are connecting the positive terminal to the drain. So the reverse biasing will be more at the drain end. So the figure will be changing like this. Okay. Okay. So I hope you got the idea. Reverse biasing in the summit, if you are increasing the VDS, reverse biasing will be more at the drain end than at the source end. അതുകൊണ്ട് സംഭവിക്കും ഈ depletion region width. This is actually depletion region width അല്ലേ? VDS തുടങ്ങുന്ന സമയത്ത് ഇതിപ്പം ചാനൽ ഈ വെള്ള വരച്ചിരിക്കുന്ന അതിന്റെ മുകളിൽ we are having channel അല്ലെ, അതിന് താഴോട്ടാണ് we are having the depletion layer. Initially when VDS value was very less, we are having a uniform width here അല്ലെ, ഈ depletion region width uniform ആയിരുന്നു. But when we are increasing VDS, what happens is that the reverse biasing will be more at the drain end, so the depletion region width will increase more at the drain end. So depletion region ഇവിടെ കൂടിയിട്ടുണ്ട് drain end when compared to the source end. And what happens when depletion region width is increased? Depletion region width increase ചെയ്യുമ്പോൾ അത് എങ്ങോട്ട് extend ചെയ്യുന്നത്? That is actually extending to the channel. The width of the depletion region, when we are saying that it has been increased, that is actually extending to the channel. That is affecting the channel width. That is more important. So when we increase the VDS value, we are increasing the reverse bias, particularly reverse bias at the drain end. So the depletion region width increase, as you said, depletion region width increase, and that increase in the depletion region will extend more into the channel. So width of the channel will reduce, and with the depletion region width will increase, and that increase will be more at the drain end. So a tapered structure, it will not be a linear structure, linear straight parallel structure. It would be having a tapered structure over here. That is, the width of the channel will be less here, depletion region width will be more here. Figure clear ആണ്. And reason പറഞ്ഞു, reverse biasing is more happening at the drain end. Is that clear? Okay. So remaining we will study in the next class. Next class also I'll be handling. You can mark your attendance. Okay, thank you.